Hello, thank you for joining us for this tutorial about coarse graining. I'm hoping to give you an overview of what coarse graining is about in this set of slides, and then Ben, who is the co-chair for this session, will go into the details, nitty-gritty details of the code and example applications that can be done with the code. First, a thank you to many collaborators I'm listing here, and some others maybe I forgot to list, for helping in different projects pertaining to coarse graining, and also funding from NASA and NSF that have allowed this research effort to be maintained. The main motivation for us to use coarse graining is as a way to map the energy pathways in the ocean. And we were motivated by this review article by Ferrer and Wunsch 2009, which identified a large uncertainty in the kinetic energy budget, and mostly due to the uncertainty of sources and sinks into the mesoscale eddy field. We don't have numbers on these question marks, and the idea of coarse graining is to help us put numbers on these question marks. So in a way, we are trying to construct a Lorentz energy cycle, similar to what is done with traditional methods using Reynolds averaging. So decomposing the flow into mean and eddy parts. Here we are decomposing the flow in length scale. So mean flow does not necessarily mean a large length. And here we are explicitly doing a length scale decomposition. And so we have kinetic energy, we have potential energy, and we are trying to map the different pathways in the ocean. So let me introduce the coarse graining approach by starting from an example of energy transfer, or the cascade, which many people in the community are working on, the energy. So this maybe for me goes back to the seminal work of Scott and Wang in 2005, and many subsequent important works that followed that, which measure the energy transfer in the ocean. Specifically, the quantity they were measuring is pi of k. This tells you how much energy is being transferred from large scales larger than this wave number k to smaller scales. K is a wave number inverse of length scale. And don't worry too much about the mathematical details here, but the definition can be found in the book of Frisch. And this kind of approach requires using Fourier analysis in box regions, and it has some limitations. So I mentioned here some of the limitations. I don't want to go into too much detail. There's another talk that I give in another session that you're welcome to listen to if you're interested. So the issue is the limitations pertain to measuring energy transfers in a box can be influenced by the choice of a box. Simply by choosing a box, you're basically discarding scales larger than that of the box. Also, doing tapering or some massaging of the data to be doing Fourier transform affects length scales, introduces gradients, etc. And the idea is that, well, scales much smaller than the box should not be affected if you're only messing up with the larger scales. That is true for the spectrum, which is the focus of signal processing and has existed for decades. So when people in signal processing do Fourier analysis all the time for decades now, no big deal. But when it comes to energy transfer, there is an issue of nonlinearity and having triadic interactions because it's cubic. It's a convolution in Fourier space, and so affecting the large scales can mess up your measurement of pi of k, even at scales much smaller than that of the box. So the method we advocate is coarse graining. Coarse graining goes back to the analysis of partial differential equations in the 1800s. So it's a basic method. In PD analysis, it's called mollification. In fluid dynamics, it may be traced to large eddy simulation modeling, specifically to Tony Leonard in 1974, who is sometimes called the father of LES, and subsequently Germano in 1992, who put that on a more rigorous basis, and then Eying, NFO, and subsequent work. The idea is you have a velocity, you convolve it with a kernel, you get out a coarse-grained velocity. This coarse-grained velocity is at position x. That describes the flow, coarse flow. So the gray structure here is a vorticity. You can see the entire velocity field at coarse-grained at scale L. So you've removed scale smaller than L, and you've kept scales larger than L by this coarse-graining operation. But you've also retained spatial information. Similar to a flower, picture of a flower here, you coarse-grain and you get a blurred flower. You still have the picture of the flower, albeit it's blurry. You still know where the center is and the petals. You don't have the fine details, but now you've disentangled the flower. If you subtract the original picture from this blurred picture, you have the fine details. So you haven't really lost information. And then you can start asking questions. We're not interested in flowers, we're actually interested in dynamics. So we want to apply this to the equation of motion. And that's what you get when you apply the coarse-graining to the equation of motion. This equation describes the evolution of these large scales. And it looks like just the original Navier-Stokes in this example, just to give you the idea. You have an additional term in blue, represents the smaller scales that have an effect, of course. They're coupled because it's a nonlinear flow. They're coupled to these large scales. So this accounts for their effect. Tau, we have an exact expression for it. So if we know these scales, we know all these scales, we can calculate it exactly. But what's powerful about this equation is that it is deterministic. It applies and describes the large scales, this gray structure, at every position x and at every instant in time. There's no statistical averaging. There's no ensemble averaging or time averaging involved. That's powerful. Another powerful aspect is that this scale L that partitions large and small is something you decide. You can make it large or small, and that by doing so, you're actually probing the coupling between different scales, as I will show you later. Okay, how do I decompose scales on a sphere? The ocean lives on a sphere. All this machinery was developed in the LAS literature on flat space, not on a sphere. You might say, wait a minute, Earth lives in 3D flat space. Why? What's a big deal? If I use a traditional definition of convolution in 3D space, this is what happens to the kernel. From the polar cap, it comes down. It doesn't quite filter or average locally around the equator. What I need to do is this. Make it rotate. So convolutions on a sphere are accomplished by rotations. This is well appreciated in applied math literature, but as far as I can tell, in the fluid mechanics literature, I couldn't find a single reference that is aware that convolutions on the sphere are accomplished by rotations. All right, this now convolution on a sphere allows me to coarse-grain a flower on the sphere. That's not enough for me because I want to coarse-grain the dynamics, not just flowers. So I want to apply it to the partial differential equation. There are difficulties with doing so. Namely, I need to make sure that this operation commutes with spatial derivatives. Why is that important? For example, if your original flow is divergence-free, I want to make sure that the coarse-grained flow is also divergence-free. And not just divergence, vorticity, gradients, all those things also apply. So you're preserving the underlying flow physics at different scales, and that's critical. If you don't do so, the dynamics becomes intractable. You cannot make sense of what you're analyzing anymore. To give you an example, this is the flow on a sphere. After filtering, it looks more blurry, as you would expect, but this is naive filtering. You're just averaging in a local region without taking into account the nuances of working on a sphere. To show you the problem, it's divergence-free before, it's 10 to the minus 11. After, it's 10 to the 4. Huge errors. You violated the divergence-free property. You've broken it down. What I found is that there's a special basis I call the Edmonds basis, and that basis is an eigen basis for the convolution on the sphere. That's a very powerful property. It is related to the canonical vector spherical harmonic basis via what I call the Edmonds transformation. It's a simple transformation that one has to apply. And therefore, one has to generalize the definition of convolution in a sphere. beyond rotation. So rotation is not enough to working with vectors and tensors, rank 2 tensors. So that's what we did in 2019. And this is a generalized convolution on the sphere. It satisfies divergence-free property. Whereas a simple naive block averaging adjacent grid cells, lat long averaging, it does not work. Using the Edmonds decomposition that I mentioned earlier is one way to do the proper coarse-graining on the sphere, but in the paper in 2019, what I showed is that this is mathematically equivalent to doing a Helmholtz decomposition of the vector field, for example, the velocity, and also higher rank tenses. And here, this is the radial part component of the vector field. This is both of these are tangential. This is the irrotational part, or the potential part of your vector field on the sphere, and this is the curl part, or this is the rotational part of your vector field on the sphere. And these are, I call the Helmholtz scalars, F, eta, and U sub r. They are scalar fields. And what I showed is that coarse-graining the velocity field or any vector field can be done by use generalized convolution, and this generalized convolution is mathematically equivalent to coarse-graining the Helmholtz scalars. And that's how the coarse-graining code that we developed does the coarse-graining, is by doing a Helmholtz decomposition and then coarse-graining the scalars. This is one way we do it. Another way is by relying on the Edmonds transformation property that I mentioned. Should mention that this kind of approach is similar to spectral modeling, but in spectral modeling, you're working in Fourier space, in spherical harmonic space. Here we're working in physical space, which is a very powerful way to look at the flow. And so therefore, in a way, we are generalizing this filtering to any kernel. We're not just doing spherical harmonics and truncating the spherical harmonic series. We are using any kind of filter, not just one that truncates the Fourier series. And that's much more general and also intuitive into the physics that's taking place, because we are looking at the flow in physical space, not in wave number space, if you will. This is what we get by coarse-graining the flow. This is original flow, larger than 100 kilometers, smaller than 100 kilometers. You can see the small scale eddies. We can analyze the energy transfer between the large and the small. This is, for example, the energy transfer between larger than 200 kilometers and smaller. Red means downscale energy transfer at the equator, from large to small scales energy transfer. Blue, such as in the Gulf Stream, means upscale from small to large, except there are some regions with persistent downscale energy transfer, which is interesting. What about wind? So the ocean moves because wind is driving it. At what scales is the wind driving the ocean? That's a very general question, very basic as well. So here I show you an image of wind work on the ocean. It's red mostly, except in the north equatorial countercurrents. You see streaks of blue, but it's mostly red, means you have a positive work by the wind on the ocean, as we expect. But at what scales is this positive work being done? It's been appreciated for a while now. Here I mentioned an important work by Zhai and Greatbatch in 2007, that circular eddies are expected to be killed by wind, to be depleted of energy by simple argument that I'm not going to go into. You can check the reference. This process has been dubbed eddy killing by Renault, who has done also very important work in this domain. The issue is that for a long time, people have been measuring power input by wind into the eddies, where eddies have been identified as a temporal fluctuation around the temporal mean. And what they found is that it's positive. You have a positive wind work. This does not match with the expectations that these circular eddies should be killed. And so there's some inconsistency, and people have tried to use eddy detection in the ocean, important work in 2016. By detecting an eddy and measuring the wind work on those eddies, people have come up with a number of minus 22 gigawatts in the global ocean. But again, this depends on how you detect eddies. What is an eddy? Is it a circular eddy? How long does it persist? So it's somewhat subjective. Ultimately, eddy killing is a spatial process, and one needs to decompose things in length scale to be able to detect it. And this is what we find by coarse graining. We see blue almost everywhere, and the eddy killing rate is minus 50 gigawatts. This is doing it the traditional way with temporal Reynolds averaging. You find a positive number consistent with previous work. We find that wind drives the ocean at scales larger than 260 kilometers. It actually depletes the ocean, the mesoscales, at scales smaller than 260 kilometers, as you can see here. The way we detect this number, 260 kilometers, is by doing a probe, a scan over all length scales, by varying this length scale L for coarse graining, and we find 260 kilometers. We identify it. We're able to analyze different oceanic regions. As an example, I show you the Agulhas, and in the Agulhas you have, even the total wind input is negative. So the wind is actually removing energy from the ocean in the Agulhas. And the reason is because of the eddy killing is so intense, even though it is driving the larger scale flow, as we show. The larger scale flow is positive, but the eddy killing is so intense that overall they have a negative wind work. Seasonality, we see that eddy killing peaks in the winter, in January, for the Gulf Stream in the north in January. It peaks, and it's consistent with when the wind peaks in the winter. This eddy killing peak in the winter may explain why the mesoscale eddies peak in the summer. And there is an explanation why 260 kilometers and why peak in the winter. We provide an explanation in this paper, in the supplementary material. Ultimately, it boils down to the spectrum of the ocean. How do you measure the spectrum in the ocean? Here I show you a coarse grain flow at 500 kilometers, coarse grain at 100 kilometers, not coarse grain. So you look at the flow at 500 kilometers, at 100 kilometers. If you subtract the energy between the two, in principle, you can get a spectrum. That's what a spectrum is, the energy at different scales. Does the idea work? It's straightforward. We show that it does work indeed. Here I show you the Fourier spectrum in black and coarse graining spectra in red and blue using two different kernels. And one has to make sure that this coarse graining spectrum is positive and conserves energy, which we showed in the paper. So there's some nuances, some measures that one has to be careful about. If you look at a region in the ocean, near the Kuroshio, for example, in a box to compare to traditional Fourier, the green is a traditional Fourier spectrum in this box, taken from the paper in Chu in 2018. The data was kindly provided by Bo Chu. And to compare, coarse graining is the orange. And you can see that the two are remarkably overlapping at small scales. They follow the same power law until you reach the size of the box, which is approximately 500 kilometers. At around 300 and 400, they start to diverge. Coarse graining starts dipping. Fourier stays going up, and you see a dip. And the thing is, coarse graining is not limited there. So we don't have to be. We can think out of the box. We're not limited by the box. And what I'm going to show you now is a result that has not been seen by many people so far. It's the spectrum over the entire ocean. This is what this is showing. The global spectrum. What you're seeing is the most prominent peak in the ocean is the Antarctic Circumpolar Current. The ACC forms a peak of the global ocean spectrum. You also see a smaller peak in the northern hemisphere due to the northern hemisphere gyres. It's arrested at smaller scales of 4,000 kilometers due to the boundaries, the continental boundaries. And the 300-kilometer peak due to the mesoscales. And here I show you the mesoscales extracted by coarse graining. And the x-axis is on a logarithmic scale. So if you integrate the area under this mesoscales between 500 and 100 kilometers, you find that it accounts for a lot of energy, the majority of the energy under this spectrum. Even though the peak is less than half that of the ACC, it just has a much more area because it's spread out over many or more wave numbers. If you look on a log-log scale, we find a k to the -1 power law scaling that has not been observed before at scales larger than 1,000 kilometers. We also find power law scaling at the mesoscales, which have been the focus of previous studies, Fourier analysis in boxes. What about seasonality? So here I show you January all the way through December in both the north and the south. And here 10 to the -1 is 10 kilometers, 100 kilometers, 1,000 kilometers. And one of the most striking things is you see the seasonality follows almost a straight line, tells us that scales 2 times as large lag by 1 month in their seasonal cycle. For example, 100 kilometers peak in the late spring, 1,000 kilometers peak in the late summer. So there's a characteristic lag time. This plot here, as far as we can tell, has not been shown before of this almost straight line behavior. What we've done is done the coarse graining on the sphere. The code is now publicly available. See our group's website. We've mapping a Lorentz energy cycle in the ocean. It's a function of scale, space, and time. And we hope our work has connections and can guide subgroup parameterizations in ocean and climate modeling. Thank you for listening.